Today, I will present our work on forward and inverse modeling of parametric dynamical system in physics-aware latent space. And as you can see, I'm at a very early stage of my PhD journey. So I will begin with the background and motivation for this work. Then I will present the reduced order forward modeling framework. And after that, I will discuss the hybrid ROMDA methods for inverse modeling. And finally, I will show some of the numerical results and conclude the presentation. So we are very interested in parametric high-dimensional dynamical systems, particularly in safety applications. So the dynamic flow case shown here is one representative case. The flow enters from inlet and interacts with the barrier, and then develops into a very high nonlinear evolution. In such systems, the state evolves in a very high-dimensional physical space, where the dynamics depend on a bunch of physical parameters, such as fluid properties, boundary condition, or geometries. So in the modeling task, the input is the parameter vector, and the output is the corresponding solution field. And what we want is to construct a predictive model. So the main challenge is that the full order simulations for the full order simulations, for instance, based on finite element or finite volume methods, are computationally demanding. So this becomes a major bottleneck when repeated simulations are needed for inverse problems or data simulation. And this motivates the use of the reduced order modeling methods. On the one hand, we have linear methods such as POD, and on the other hand, we have nonlinear methods such as deep learning based CNN based autoencoder. So following the standard CAE, we introduced the OACAE proposed by Fukami and Terra. The key idea here is to augment the standard CAE with an additional branch. While we reconstruct the physical fields, this branch also help us to encourage the latent variables to remain informative with respect to physical measurements or system parameters. So in this way, the latent representations are distinguished for different parameter settings and evolution scenarios, and which yields a more regular latent space for us. And the last part of the background introduction is parameter calibration using data simulation. So in our setting, we can start from a background of the parameter, and together with the observations in solution space. And what we also have is the predictive model that links the parameter space and the solution space. And then we can use the data simulation to help us to update the background parameter and to yield the corrected or analysis parameter. So the main goals of our research is to develop an efficient variational DA framework for parameter calibration using a deep learning-based reduced order modeling circuit. And secondly, we want to also see the benefit of the OACAE within the proposed ROMDA framework. And thirdly, we want to also compare our framework with a POD GPR circuit coupled with InKF as the baseline. In this presentation, I'm not going to drop too much words on the baseline. For details, here is the reference of Lume, the circuit-based ensemble DA. Now I move to the reduced order modeling framework, OACAE MLP. The main idea here is to construct a latent space and then perform efficient prediction in that latent space. And it is worth mentioning that we embed the time index into the parameter vector. So during the training and inference, we used here the data pairs of mu t and x mu t. The workflow has 2 training stages and 1 inference step. In step 1, we train an autoencoder to reconstruct the physical space, and at the same time, we train an MLP here to output the parameter, which is associated with each velocity field over time. And this can give us a physics-aware latent space. In step 2, we train another MLP model that maps the parameter to the latent space and then decode it back to physical field. And finally, during the inference, we can use the MLP trained in step 2 and the decoder trained in step 1 to directly construct the predictive model and start from new parameters to the full field directly from the new parameter. And for the standard CAE MLP model, the physics-aware branch can be removed by setting the corresponding weight coefficient alpha to 0. So after building the surrogate, the next step is to couple it with the variational DA framework. Here we illustrate how the parameter vector is mapped and through the surrogate and to the solution field. For a single time step assimilation, we can use the 3D wall, the objective background term and an observation term. So the observation term can penalize the mismatch between the observed field and the surrogate prediction at one time step. So for multi-time step assimilation, we can use the structure is very similar, but now the observation mismatch can be accumulated over multiple time steps. Well, in practice, the background mean and covariance error are estimated empirically from the parameter training dataset, and the observation error covariance metrics are estimated from the prediction error of the surrogate model on the training dataset. The optimization is performed through the TalkDA package. Package, and this is the first Python package for integration of DA, and for the integration of DA methods with neural network functions, whether it is the transformation models or the forward models. Well, this is very important in our present setting because we need to embed the deep learning based RLM directly into the assimilation loop. Well, I now move to the numerical results of the present work. The main benchmark here used is the Denflow case from the CFD bunch. This dataset consists of full flow field data defined on a uniform 64 by 64 with these snapshots and these parameter configurations, and we have among all the cases we have used 173 cases for training, and the rest are reserved for testing. And each snapshot in the data is associated with a 6-dimensional parameter vector encoding the boundary conditions, fluid properties, and geometry, and also the time index. And here are 100 property cases, and here are 100 cases varying property, and 50 cases varying geometry, and 67 cases varying the boundary condition. And this is a figure showing the DA test setup. So we can think of the test set as a grid indexed by case and time index. This allows us to evaluate our framework in 2 ways. Firstly, we can perform the DA test on all time steps for one selected parameter configuration, and we can also select a one-time step and then do our DA framework on all test cases. So let us first look at single type assimilation. Here we compare 3D-VAR with InCAV using a single observation. This table reports the relative error of calibrated parameters averaged over all assimilation time steps of the selected case. So we see that the data simulation can improve over the background estimate, and the variational DA is better than the INCAF baseline. Well, in particular, the OSAE-based 3D war can outperform the CAE-based 3D war. Well, to better understand these results, we recall the 3D war cost function. In variational DA, here is the 3D war cost function. The primary goal is to approximate the minimizer of the cost function. Well, since the predictive model GMLP and trained here is not perfect, even the true parameter may not reach the minimum of this cost function. Therefore, a successful assimilation result should at least produce an analysis parameter whose loss is not higher than the one associated with the true parameter. And this is a necessary condition to ensure the success of the variational DA procedure. And also in our setting, the observation term is much larger than the prior term, since the matrix R is estimated from the surrogate prediction error, and this error can be very small. When the model is trained well. So as a result, the optimization is mainly driven by the second term, when the R inverse can give a very large weight to this term. So we want to compare the observation loss of the parameter and the analysis parameter to evaluate the performance of variational DA. Here are the 4 plots that compare the observation loss trajectories evaluated at the true parameter and the analysis parameter, and all the analysis parameters that we have by doing 3D war on every time step of the selected case. For OSAE, we can see that the analysis loss curve stay consistently below, yet close to the truth curve. Well, in contrast, the CAE here, we can see that the mismatch between the two curves is quite larger, and the data simulation performance is not very stable. Next, we consider the multi-time step assimilation by using the 4D war with 2 observations. Here is the 4D war test setup. We have selected 10 observation pairs along the time axis, which can be easily compared with 3D war. Gives us 10 independent 4D war tests. And we recall that the observation loss term used in here in the function of 4D war considers considers the mismatch of observation at more than 1 time steps. Here is the 4D var. Here is the 4D var loss curve. Well, in the damp flow case, we can see here, even though the 3D var curve can produce a loss curve that is very clear to the truth curve, the 4D var can still reduce this, and this means the parameter calibrated by the 4D var can even produce a lot more accurate prediction compared with the result of 3D var and the truth parameter. And this is even clearer when in the cavity flow case. So the improvement is even clearer. The 4D var gives a lower and more consistent loss trajectory than 3D var. And These laws produced by 4D can remain better aligned with the truth curve. We then evaluate the 10 simulation tests by measuring the mean relative error over the entire prediction evolution. Since the 4D the 4D pairs used here come from the same evolution as the 3D test, it is easy to make a direct comparison between single time step simulation and multi-time step simulation. But for each simulation test, based on the parameter identified in that test, we first compute the relative error at every time step of the evolution, and we then average it over time. And then we average this quantity over all test cases. We see that when OACE MLP combined with 4D VAR, the result can achieve an even lower error than the prediction with the true parameter. And while OACE MLP combined with 3D VAR, the result can still remain a close error to the true parameter.
2 minutes.
This indicates that the parameter calibration is beneficial not only at the simulation points, but also for the global evolution, and that the overall prediction quality can be significantly improved using only one or two observations. And here is a field visualization and error maps at a certain time step of the combination of OACE MLP DA model. And for the last part, we test the robustness of our framework across different evolution scenarios, fixing the observation time step. Well, here are the recovered parameter all test cases. Here we have 44 test cases. Well, starting from the same background error, start from the same background value, the 3D VAR methods recovers the parameters that are generally closer to the truth than those obtained with the baseline. Well, to quantify the performance in parameter space, we compute the mean square error and standard deviation across all test cases. This also allows us to compare the OACE-based method and the CAE-based method. So we see that the OACE-based method achieves lower error and lower uncertainty. Which indicates a more accurate and stable behavior of the variational DA. And more importantly, the same trends can be seen in the physical space, in the prediction in the physical space. Here again, we first compute the relative prediction error at every time step of the evolution and average this over time. And then we continue to average this quantity over all test cases. Here we have 44 cases. We see that the parameter calibrated by OACE-based 3D VAR can even yield a physical space prediction error and uncertainty that are slightly lower than the true parameter when compared with the ground truth field and the truth when compared with the ground truth field. And this further confirms the benefit of using OACE-based framework, which can very successfully achieve robust variational DA across different evolution scenarios. In case you are interested in a broad range of machine learning and data simulation methods, please refer to this paper. And thank you for your attention.
Okay, great. Thank you, Qiyao. So I don't see any questions at the moment in the Yo pad. So I think in the interest of time, we'll probably just move on because we are a bit behind schedule. But if you do for Qiyao that you think about.
Thank you very much.
Yeah,